On July 25, 2000, Air France Concorde Flight 4590 was a planned charter flight from Charles de Gaulle Airport in Paris, France, to New York's John F. Kennedy International Airport. There were 100 passengers, 3 flight crew, and 6 cabin crew on board. Many of the passengers on the flight began their travel in Germany, and once in New York were planning to transfer to a cruise ship and visit the Caribbean islands. The captain, stationed in the left seat, was the pilot flying, and the first officer, stationed in the right seat, was the pilot observing. A flight engineer was stationed in the flight engineer's position behind the first officer. Planned speeds for the takeoff were V1 of 150 knots, VR of 198 knots, and V2 of 220 knots. Takeoff began from runway 26 at approximately 2:43 p.m. local time. Full thrust was used for the takeoff as the airplane's weights and fuel loading were near maximums. The aircraft accelerated normally, passing through 150 knots 33 seconds after beginning the takeoff. Approximately 7 seconds after V1, the number 2 tire of the left main landing gear struck a piece of sheet metal debris that had fallen from a Continental Airlines DC-10 during a takeoff 5 minutes earlier. The number 2 tire of the Concorde disintegrated, sending high-speed tire fragments into the lower wing surface and left wheel well area. Almost immediately, the number 5 fuel tank lower surface ruptured, resulting in a massive fuel leak and fire. Engines 1 and 2 began to surge, believed by investigators to be due to either ingestion of hot gases, debris from the tire failure, or both. Engine 1 recovered, but Engine 2 continued to malfunction. The takeoff trajectory began to drift to the left, believed by investigators to be due to the loss of thrust on the left side of the airplane. The pilot continued the takeoff and rotated the aircraft as the plane passed over the left edge of the runway, striking runway edge lighting as the plane lifted off. An air traffic controller observed the fire coming from the left wing area of the Concorde and contacted the flight crew, advising them of large flames coming from behind the aircraft. Shortly after liftoff, an engine fire warning sounded for engine number 2, followed by the crew shutting it down. The crew attempted to raise the landing gear, but the gear would not retract, believed by investigators to be due to damage caused to the wheel well area by the tire failure. The airplane climbed to an altitude of 200 feet and a speed of 200 knots, but was unable to accelerate or climb past that. The airplane remained at this altitude, speed, and heading for nearly a minute after liftoff, while the fire continued to damage flight control surfaces on the left wing. The ground proximity warning system sounded several times during this period. At approximately 2:44, the number 1 engine failed and the airplane lost control and crashed into a hotel several miles from the end of runway 26. The airplane burst into flames and both the airplane and hotel were completely destroyed. All 109 passengers and crew on board were killed. An additional 4 persons on the ground were killed and 6 were injured. Investigators determined that the takeoff roll of Air France Flight 4590 progressed normally until a speed of approximately 180 knots had been reached, a speed well past the planned 150-knot V1 decision speed, but well short of the 198-knot rotation speed for this flight. It was established that, at this point in the takeoff, the number 2 tire of the Concorde's left main landing gear struck a piece of sheet metal that had fallen from a Continental Airlines DC-10 that had taken off from runway 26 5 minutes earlier. It was learned that the sheet metal debris that Flight 4590 struck was a thrust reverser seal from the number 3 engine of the DC-10. Investigators concluded that the number 2 tire of Flight 4590, upon striking the piece of sheet metal, immediately disintegrated, sending high-speed tire debris into the bottom of the left wing and into the wheel well area. Almost immediately, multiple areas of the number 5 fuel tank bottom failed, resulting in a massive fuel leak. The fuel leak quickly ignited, believed to most likely have been the result of electrical arcing from damaged wires in the wheel well area or possibly from hot engine parts. Extensive analysis was conducted of debris recovered from the runway, evidence found at the accident site, marks left on the runway surface, component testing, and analysis of the aircraft's voice and flight data recorders. Detailed metallurgical analysis of a large piece of the No. 5 fuel tank bottom recovered from runway 26, as well as other pieces of the tank bottom recovered from the accident site, indicated that the tank failure mechanism was from internal overpressure, not from penetration by tire debris. There were also small inward punctures of the tank surface found on wreckage from the accident site, but the large tank openings of the No. 5 tank were determined to be outward failure modes. This outward failure mechanism had never been observed on civil aircraft before, and to understand its cause became the central focus of the investigation. Extensive studies were performed on the tank failure dynamics, including complex computer analyses, multiple types of tank impact testing, and theoretical modeling. Although it was not possible to pinpoint exactly what caused the outward tank failure to occur, results of these efforts suggested that the most likely cause was the combined effects of at least two complex mechanisms occurring simultaneously. This animation is a simplification of two of the mechanisms believed by investigators to be the most likely to have occurred. They are shown here in order to help understand the general concepts and are not intended to be precise depictions of the tank failure causes. The first general process involves what investigators referred to as the continuity effect, or a physical condition where a deformation inward results in a corresponding outward deflection in the immediate area next to the inward deflection. The interface area where these two deflections occur, but in opposite directions, becomes the origin of locally strained material and results in a weakened area in the tank bottom due to the highly strained condition. The second physical process identified by investigators was referred to as a hydrodynamic pressure surge and is a consequence of an essentially full fuel tank, sudden inward deflection, and the presence of an incompressible fluid, jet fuel, which is being displaced by the deflection. The rapid inward deflection and incompressible jet fuel being displaced causes a rapid pressure rise, especially in the immediate area adjacent to the deflection. When both processes occur simultaneously, the increasing area of strain and increasing outward pressure eventually leads to the weakened area fracturing outward. This results in partial or complete release of the tank bottom section as observed by examination of the No. 5 fuel tank panel recovered from runway 26. Investigators also concluded that an additional pressure increase may have come from small, high-speed fragments that may have penetrated the tank surface and contributed to the overall internal pressure increase. Due to the extent of damage in this area of the wreckage, this hypothesis was not able to be identified with certainty, nor was identification of the penetration objects. In order to help understand this complex failure process, the FAA has created a simple high-speed video as a demonstration of both the continuity effect and the hydrodynamic pressure surge of an incompressible fluid in an essentially full container. For this demonstration, a ball is directed into the side of a full plastic jug of water at approximately 70 miles per hour. As the ball begins to make contact with the surface of the jug, the very slight inward motion begins to move the area adjacent to the impact slightly outward, this being a result of the continuity effect process. The slight outward motion of the area around the ball can be observed and results in the aluminum foil initially moving slightly inward into the neck of the jug as the overall volume of the jug begins to increase. As the ball continues to deflect into the tank surface, eventually the inward motion reverses the overall tank volume being deformed, and a hydrodynamic pressure surge rapidly increases, leading to rupture of the foil. This demonstration is not intended to precisely replicate the complex failure mechanism of the Concorde No. 5 fuel tank surface, but is only included here as a visual aid in helping understand the process of the continuity effect as well as the hydrodynamic pressure surge within a volume containing an incompressible fluid.